Electrostatics, Coulomb's law. If there are two charges Q1 and Q2 at separation R, then force of attraction or repulsion between them is directly proportional to product of the charges Q1 into Q2. And F is also inversely proportional to square of distance between them. If we combine the two, we get F proportional to Q1 Q2 divided by R square. We need a constant here. So we write F equal to 1 upon 4 pi epsilon naught Q1 Q2 divided by R square, where 1 upon 4 pi epsilon naught is equal to 9 into 10 to the power 9 Newton meter square divided by Coulomb square. And epsilon naught is 8.85 into 10 to the power minus 12, and unit is just reverse of 1 upon 4 pi epsilon naught. That is Coulomb square divided by Newton meter square. Now, vector form of Coulomb's law. If charges are of like nature, suppose Q1 and Q2, both are positive. That is Q1 into Q2 is greater than 0. If both are negative, still this condition will hold. So there will be repulsion, and repulsion will be written like this. So this will be F12 and this will be F21. Now F12, force on charge 1 due to second charge, is given by Q1 Q2 divided by 4 pi epsilon naught R square times unit vector R21, where R21 unit vector is equal to vector R21 divided by its modulus. And F21, force on second charge due to first charge, will be equal to Q1 Q2 divided by 4 pi epsilon naught R square times R12 vector, where R12 is equal to vector R12 divided by its modulus. Since R21 and R12 are oppositely directed, so we can say these are unit vectors, so their modulus will be unity. So R21 is negative of R12. So from equation 1 and 2, we get F12 is negative of F21. To every action, there is equal and opposite reaction, which is Newton's third law. Now, there are certain things that you have to memorize. Units of charge. You know, Coulomb. There are other units also. One is ESU. This is also called state Coulomb. 1 Coulomb equal to 3 into 10 to the power 9 state Coulomb. It is also written as ESU. And 1 Coulomb is also equal to 1 upon 10 F Coulomb. This is called electromagnetic unit, EMU. Now one more thing, the range of Coulomb's law. So Coulomb's law or Coulomb's force is valid from 10 power minus 15 meter to 10 to the power 18 meter. So this is range of Coulomb's force. Now, next thing is superposition principle. Suppose there are many charges and we want to calculate the force on particular charge. Suppose this is Q0, another charge is Q1, next charge is Q2, next charge is Q3, etc. And the separation between first two is R1, then this is R2, then next one is R3. In that case, force on Q0 F is equal to Q0 Q1 divided by 4 pi epsilon naught R1 square plus Q0 Q2 divided by 4 pi epsilon naught R2 square plus Q0 Q3 divided by 4 pi epsilon naught R3 square and so on. Or we can take common Q0 upon 4 pi epsilon naught. Then we can write Q1 upon R1 square plus dot 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 or Qi divided by Ri square can be written like Q0 divided by 4 pi epsilon naught sigma I equal to 1 up to n Qi divided by Ri square. Now, next point is electric field. So, F equal to Q1 Q2 divided by 4 pi epsilon naught R square. If we write Q1 as Q0 and Q2 as Q, then F will be equal to Q0 into Q divided by 4 pi epsilon naught R square. Now we divide it by Q0. So F upon Q0 is equal to Q divided by 4 pi epsilon naught R square, which is equal to electric field. So relation is F equal to Q0 times E. Unit E has two units. One is volt per meter, another Newton per coulomb. Now, superposition principle. If there are many charges, then electric field at a point will be sum of individual effects. E will be sum of E1 plus E2 plus dot 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 till En. Now, next point is continuous charge distribution. Continuous charge distribution means line charge distribution or linear charge density. So linear charge density means charge divided by length. It is denoted by a lambda, which is Q upon L. Unit will be Coulomb per meter. Then surface charge density is charge divided by surface area. It is denoted as sigma, which is Q divided by area. Then volume charge density, that will be charge divided by volume, written as rho equals Q divided by volume. Now, let's see electric field due to a charged ring. This is a charged ring placed perpendicular to the x-axis, and this is center. The radius of the ring is a, and the charge is distributed over its periphery. And we have to find out electric field due to this ring at point P, which lies on its axis. Now, we consider one element dl, due to which the electric field will be directed like this. And then we consider another length element dl diametrically opposite, whose electric field will be directed like this. Similarly, we can consider many such elements. So here, these two will have effect like this. So dE will have one component dE cos theta in this direction. Another component will be dE sin theta in this direction. Now consider this dE. This angle is also theta. So dE cos theta will be in this direction and dE sin theta will be in this direction. Clearly, dE sin theta component will cancel out. This will happen for each such elements. So we can say that electric field will be due to cos theta components only. Now, since charge Q is distributed over the periphery or over the ring, so we can say charge density lambda. So lambda will be equal to Q divided by length of ring 2 pi a. Now, for this small portion dl, suppose charge is dq, that dq will be Q divided by 2 pi a times dl. And due to this dq, this is dE is the electric field. So dE can be written as dq divided by 4 pi epsilon naught, and this distance is r, so r square. As we have discussed that net electric field will be due to cos theta components only. So we can say E equal to integration, we consider the whole ring. So 0 to 2 pi a dE cos theta, that is 0 to 2 pi a dE is dq divided by 4 pi epsilon naught r square into cos theta. And the cos theta will be based upon hypotenuse, that is x upon r. So, and r will be equal to x square plus a square under root. So what do we get? We will get E equals integration 0 to 2 pi a dq, that is dq can be written as q times dl divided by 2 pi a. So q times dl divided by 2 pi a times 4 pi epsilon naught. Cos theta is x upon r, that is x upon r cube. So, and r is this root of x square plus e square. So we can write it like x square plus a square whole power 3 by 2. Now we integrate. So integration dx gives x. Similarly, integration dl will give L. And if we put limit here 0 to 2 pi a, so this L will become 2 pi a. So our result will be qx divided by 2 pi a times 4 pi epsilon naught times x square plus a square whole power 3 by 2 times integration dl This term will give 2 pi a. So 2 pi a, 2 pi a will cancel out. So we have got the result as E equal to qx divided by 4 pi epsilon naught times x square plus a square whole power 3 by 2. Now, if we do some approximation, like we say x square is greater than a square, in that case, we will neglect x square. So in the denominator, we will get x square whole power 3 by 2. So 2 will cancel out x cube. And here there is already 1x. So ultimately, our result will be E equal to 2x divided by 4 pi epsilon naught x cube, which is equal to q divided by 4 pi epsilon naught x square. It is same as electric field due to point charge is given by q upon 4 pi epsilon naught r square. So this was our required result. Now let's consider one more case. Electric field at the center of thin charged semicircular ring. This is semicircular ring which is charged. Now its radius is a. We have to find out the electric field at its center. We consider small length element dl making angle d theta. So dl equal to a d theta, arc upon radius equal to angle. Here arc is dl, radius is a, and angle is d theta. Now charge per unit length is suppose lambda, then charge on portion dl will be equal to, suppose this is dq, lambda dl, and we put the value of dl as a d theta. So dq equal to lambda times a d theta. Now we consider electric field due to this small element. So this is dE. Cos theta component will add up and sin theta component will cancel out, because here in this direction there will be dE sin theta due to this dE. And similarly, if we consider another length element dl here, so electric field due to this element will be dE in this direction. So cos theta component will be in this direction and sin theta component will be in this direction. Hence, we can say that if we consider any element dl here, so another element dl will be here, whose sin theta component will cancel out and only cos theta component will be the cause for electric field. So now we can say that dE will be equal to dq divided by 4 pi epsilon naught, distance is a square, and dq equal to lambda a d theta divided by 4 pi epsilon naught a square, which is lambda d theta divided by 4 pi epsilon naught a. Now, net field, as I told you, it is due to cos theta component. So E will be equal to integration from here. This limit will keep minus pi by 2, and this limit we keep plus pi by 2. So we write minus pi by 2 to plus pi by 2, and then dE cos theta. We put the value of dE as lambda d theta divided by 4 pi epsilon naught a. So we get minus pi by 2 to plus pi by 2 lambda d theta divided by 4 pi epsilon naught into A times cos theta. Now, integration of cos theta will give sin theta. So from here we can take common lambda upon 4 pi epsilon naught a, and then we integrate this integration cos theta d theta, so that will give sin theta. Then we will put limit. So I'm writing it on the next page. So lambda divided by 4 pi epsilon naught a, and this will give sin theta, and limits are minus pi by 2 plus pi by 2. So the limits. So we get E equals lambda upon 4 pi epsilon naught a times sine pi by 2 minus sine minus pi by 2. So this will give lambda upon 4 pi epsilon naught a. Sine pi by 2 is 1 minus sine minus theta gives minus sine theta. So from here this will become plus 1. So 2 lambda divided by 4 pi epsilon naught a, which is equal to lambda upon 2 pi epsilon naught a, which is our answer. Thank you for watching.